Welcome to session 3 of Unit 4. And in this session, we'll be evaluating the standard cell potential of galvanic cells. By the end of the session, you should be able to write an oxidation half cell equation, write a reduction half cell equation, and calculate the overall standard cell potential of a cell and state the significance of its sign. So, to make possible a consistent table of values of half cell, it is internationally accepted that the EMF of the hydrogen cell is equal to 0. So like I said in our previous session, the standard cell potential of hydrogen is 0. So the standard hydrogen potential or cell serves as the reference electrode. So any other half cell is compared with that of the standard hydrogen cell to determine the EMF. So the EMF of other half cell can then be measured relative to that of the EMF of the hydrogen cell. So basically, when these measurements are done at standard conditions at temperature 25 degrees Celsius and with an effective ion concentration of 1 molar and at atmospheric pressure of 1 atm, then we do that under standard conditions. So the value obtained is called the standard electrode potential, and the symbol, like I had earlier on illustrated, is represented as E subscript 0. So the formula for calculating the standard cell potential is the standard cell potential is equal to that of the oxidation minus that of the reduction. Now, a galvanic cell consists of two half cells. We have the convention, in other words, the convention in writing such a cell is to put the reduction cathode on the right hand side and then the oxidation on the left side. For example, we could have it this way. So it is not always necessary that it is this way. So most often than not, the oxidation half comes first and the reduction comes second. So in some books, you're likely to see oxidation first before the reduction half cell. So basically, when you see this, then we can say that this is undergoing oxidation, reduction, and this is undergoing what? Oxidation. So in this particular example, the hydrogen is undergoing oxidation and then the zinc is undergoing reduction. So at concentrations of 1 molar and the pressure of 1 atm, the voltage difference between the two electrodes will be, so that has been done and then that has been experimentally determined, and the value measured was negative 0.76 volt. So which means that the zinc electrode has a standard electrode potential of negative 0.76 volt. So the conditions specified above are called the standard conditions, which we said earlier on. And the EMF so obtained is a standard reduction potential. Standard reduction potential. Now, let's take an example. What is the potential for the cell zinc to the power 2 at concentration of 1 atm and then copper as well? So from a table of standard reduction potentials, we have the following value. So in our previous session, I gave you the table, and you can also make reference to books for these values. So reduction or copper is undergoing reduction and the zinc is undergoing oxidation. So all you have to do is to add 1 and 2 to yield this. So the reduction plus oxidation will give us 1.0 V. So the standard cell potential is represented as dE, which we said earlier on. So if we are calculating for this, then the standard potential of the cell, of this particular cell, is equal to 1.100 V. So we realize that the positive potential confirms your observation that zinc metal reacts with cupric ions in solution to produce copper metal. In other words, zinc can actually displace copper in the solution. So as a session review, write the oxidation and reduction half cell of redox reactions. That is what we've been able to do so far, and we've been also able to calculate the standard electrode potential of a cell. So in which cell does not take place. So now look at this example. In which cell does reduction takes place? The right hand cell or the left hand cell in the notation. So look at the notation very well. Where does oxidation take place and where does reduction take place? Thank you, and I hope to see you in the next section.